So what we're going to do today really is just a review of some of the high points of SN2 and SN1 reactions, which I know we go over in organic 1. Okay, so a lot of this should be review. SN1, SN2, what does that mean? Well, remember the S stands for substitution, the N stands for nucleophilic, and the number, the 1 or the 2, stands for the order of the reaction, whether it's a first order reaction or a second order reaction. Okay, so we'll actually talk about the second order reaction type first, the SN2. But either way, it's a nucleophilic substitution reaction. Okay, so substitution, what's going to happen is you just replace a leaving group with a nucleophile that's incoming. So a nucleophile trades places with a substituent. So if you have a substrate like this, where you've got some organic compound and it has a leaving group, which we're just calling X, the nucleophile comes in and just replaces it. So the leaving group leaves, and the nucleophile forms a bond with the substrate. That is a nucleophilic substitution reaction. As I said, there are two types that we focus on, SN2 and SN1. So just some more of the terminology. A lot of these notes are actually just straight, copy and paste from what I teach in organic 1, so you've seen it all before. But the substrate is just what you're transforming. All right? It is the major reactant that's undergoing the transformation. We just want to get used to the terminology. Substrate's what you're transforming. The nucleophile is what's coming in and attacking. The electrophile is what's being attacked on the substrate. It's the specific atom on the substrate that's got that partial positive charge, sometimes even a formal positive charge. And then the leaving group is, big surprise, the thing that's leaving, okay? All right, so there we go. A leaving group is the atom or ion, a group of atoms, right, that is displaced in the reaction. Okay, so as I said, we'll focus on the SN2 reaction first. So in this mechanism, these are reaction mechanisms, the explanation of how the transformation occurs. So in this mechanism, the rate of the reaction depends on both of the reactants, the nucleophile and the substrate. Okay, so remember, we can express that with a rate law. So writing in an equation type way, what we just said in the above bullet, the rate then is equal to some rate constant K multiplied by the concentration of the substrate and the concentration of the nucleophile. And one other thing to remember from our discussion about SN2 reactions is that it inverts the electrophile. So whatever atom is being attacked, everything else that's attached to that atom gets flipped like an umbrella, flipping an umbrella inside out. It gets inverted. So if that happens to be a chiral center, that's the only time where it really matters, is if that electrophile is a chiral center, then that chirality gets switched. For example, if it was S, it becomes R, or vice versa. So the chiral center participating in the reaction gets inverted. Okay, and this is just a video animation that shows you how this occurs. So the big green ball is the nucleophile. It attacks from the backside, forms a bond with the substrate, spits out the yellow ball, which is your leaving group, and you'll notice it's a little bit challenging to notice in this animation, but those white balls, they kind of flip their orientation and go out. They're pointing in, now they're pointing out, so it gets inverted. That's an SN2 mechanism. All right, and it just shows how it does depend on each reactant, how you got the substrate and you got the nucleophile, and they've got to collide. So the number of those collisions is going to be dependent upon the amount of substrate you have, as well as the amount of nucleophile you have. So that's why the rate is dependent upon each one. Okay, so these are just some graphs to help, again, remind us of some things we learned in Organic 1 and back in Chem 2 when we talk about reaction kinetics, that this quantity right here, this activation energy symbolized with the delta G double dagger, okay, that is your activation energy. And so the reaction will proceed faster if it shrinks. So for example, if we go from this black curve to this magenta curve, then that activation energy shrinks because it's the energy barrier from the bottom to the peak, from the bottom to the peak. Okay, so if you do something to make that smaller, then your reaction is going to proceed faster. Now, there's two ways to do that. As I said, you can either change the energy from the initial conditions. Right here, you go from this lower energy black curve to this higher energy magenta curve. You've effectively decreased the activation energy. But the other way to do that is to lower the activation energy associated with the transition state. So in this case, it's like we're going from the magenta curve down to the black curve. Okay, so that also is a way to shrink that activation energy. So either one of those things are going to cause the reaction to go faster because you're lowering that activation energy, that energy barrier. Okay, so what again, that's pretty much a review. What I want to remind you of more importantly right now is the factors that will affect that activation energy. One of them being the steric effects, also the type of nucleophile used, the type of leaving group that's on the substrate, and also the solvent choice will impact the reaction kinetics for an SN2 reaction type. Okay, so we're going to go through each one of these, talk about them in a little bit more detail. So that first variable, the steric effects, it has to do with crowding around the electrophile because we've got to form this partial bond from that backside attack between the nucleophile and the substrate. So a partial bond is formed between the incoming nucleophile and the alkyl halide carbon atom. We're assuming here that our substrate is an alkyl halide, therefore your electrophile is that carbon atom that's also attached to the halogen because it's got that partial positive charge on it. So partial bond is formed between the incoming nucleophile and the alkyl halide carbon atom. Okay, but that's just challenging, it's difficult when there are other alkyl groups blocking the way. Okay, this is difficult when other substituents block the approach. So it stands to reason that the more alkyl groups that are connected to the electrophile, the slower the reaction. It becomes more crowded. Fancier term for that is steric hindrance. There's more steric hindrance. So ultimately it leads to a slower SN2 reaction. So the more alkyl groups that are connected to the electrophilic carbon, the slower the reaction. Okay, so this is just an example of what we're talking about. That if all those words don't make a lot of sense, a lot of times a diagram like this helps. So if you look at our substrate, we just have an alkyl halide. We have some R group. Remember, that's just a bunch of carbon and hydrogens and maybe some other stuff. In this case, attached to a chlorine. Okay, so I'll trace on here what's going on. So your nucleophile is going to be the chlorine in this case. This is our nucleophile. And that carbon in the R group is going to be your electrophile because that's got the partial positive charge, and the bromine's got the partial negative charge because of the polarity of this bond. So your nucleophile is going to come in and attack the carbon on your substrate, and then it's going to break that bond between the carbon and the bromine. The electrons are going to get dumped onto the bromine, transform that into the bromide. So that's why, that's your leaving group. And you form that new bond between the nucleophile and the electrophile and the substrate. Okay? Well, this just shows you if I change what the identity of that substrate is, if I change the identity of that R group, how it affects the rate. So if we just start with this, this is kind of our standard. We'll call that relative reaction rate 1 of 1, the neopentyl, where in this case, the electrophile, that partially positive carbon, has got 2 hydrogens on it and then a T-butyl group. Okay? Well, that T-butyl group is really big. It's very bulky. Well, if I, sort of reduce the size of that by making it actually 2 methyl groups, so I replace one of the hydrogens with a methyl group, but I change this, I kind of, make this a little smaller by making it just a methyl group, it speeds up the reaction 500 times. If I cut that back to just 1 methyl group, it speeds it up 40,000 times. If I just have 3 hydrogens, then, it's 2 million times faster. But you can make it smaller if instead of hydrogens, I make all 3 of the methyl groups. So therefore it would be a tertiary carbon, that's the substrate, the electrophile in the substrate, then it slows it down to less than 1. Okay, so these are all just different ways to make the crowding worse or better. And you can see how it affects the reaction rate. Okay, and this is just, again, just a little space filling models to maybe help you see it. It's just that carbon, which is the gray sphere, is a lot more accessible over here on the right with that methyl group than it is with the tertiary carbon. These three gray balls that you see, those are not even your electrophile. Those are just methyl groups that are in the way. Your electrophile is buried in there, so it's going to be hard to reach. Okay, so that's the steric effects. Now let's talk about the nucleophile, how it will affect the rate of the SN2 reaction. So the nucleophile is a Lewis base, and therefore it's a pair of electrons looking for something positively charged. So that Lewis base can be either neutral or negatively charged. So the nucleophile is neutral or negatively charged. It's always a Lewis base. And the trends that we see in the strength of the nucleophile follow along these lines. So first of all, the strength of the nucleophile roughly follows the same trend as the strength of bases, but there are a lot of exceptions to that. It's okay to kind of apply that thumb rule, but be ready for a lot of exceptions. And you'll see that in the chart that's coming up. There's a chart that'll be in the presentation, but it's not in your notes, but we'll just talk a little bit about it. So stronger nucleophiles are typically stronger bases. Stronger bases are typically stronger nucleophiles, but there are some exceptions. Okay, something we have talked about before, that the strength of the nucleophile increases as you go down the periodic table. So for example, sulfur is below oxygen on the periodic table. So nucleophiles that act through a sulfur are stronger than nucleophiles that act through an oxygen. And this one's kind of duh, that since a nucleophile is something that's got negative, it's got electrons and it wants to react with something positive, if the nucleophile happens to be negatively charged, that's going to be a stronger nucleophile than something neutral. So nucleophiles with a negative charge are generally more reactive than those that are neutral. Okay, so again, I promise you this table, this is not in your handout, but some things you can look for. So if you compare like water versus hydroxide, they're similar nucleophiles, but the hydroxide has a negative charge, and it's 10,000 times more reactive than a water molecule. Okay, compare hydroxide now with HS minus. So hydroxide versus HS minus, so you see the difference is oxygen versus sulfur. So the HS minus is 125,000 times, or I guess that would be 12.5 times more reactive than hydroxide. Okay, because as you go down the periodic table, your nucleophile gets stronger. And in general, you can see that things that are charged, all these guys that down here that are charged, are stronger nucleophiles than these two up here that are neutral, H2O and ammonia. So that just makes the point that nucleophiles that are negatively charged are stronger they're more reactive than neutral nucleophiles. Okay. All right, so now let's talk about the leading group. So this is another factor that will affect the rate of an SN2 reaction. So any sort of leading group that will stabilize the negative charge in the transition state, that's what the capital T, capital S, remember, that's what that stands for, the transition state. Those are going to be the best leading groups. And the better the leading group, the faster the SN2 reaction, more reactive the substrate. So what kind of things will stabilize that negative charge buildup in the transition state? Well, one is resonance. If you could draw different resonance forms of your product leading group, that means it's going to be a more stable, independent ion. And so it's going to facilitate that reaction. But the other thing is polarizability. And remember that the trend with that is the bigger the species, the more polarizable it is, because that electron cloud can get sloshed around a little easier. That's what polarizability is. How easy is it to distort that cloud of electrons? If it's easy to distort the cloud of electrons, we call it highly polarizable, and that's more stable if it has to adapt, if it has to take on a charge, usually a negative charge. Okay, so for example, if you go down the periodic table, like fluoride, chloride, bromide, iodide, those are better leading groups as you go through that series. And it's because each of those halogens is more polarizable than the previous one. So chloride is bigger than fluoride, it's more polarizable, so it's a better leading group. Bromide is even better, and iodide, which is near the bottom of the periodic table, is even better. So this one, TOSO, remember that's tosylate, and the thing there is that it's stabilized by, I don't have the structure in the notes, but it's stabilized by several resonance forms. You can push electrons around and draw several resonance forms, and so it's a really good leading group. If you want something to leave, somehow convert it into a tosylate, and it will be a good leading group. Okay, things that are really bad leading groups are like a hydroxide or an NH2 or a methoxy group, alkoxide group. Okay. But in general, just a couple things that you can always just, again, more thumb rules you can kind of hang your hat on. If it's a weak base, then it's going to be a good leading group. And so, well, what's a weak base? Well, that would be like the counterion from a strong acid. Like HCl, you remember it's a strong acid. So the conjugate base would be Cl minus. HBr, same thing. HI, same thing. All those are strong acids. So they're conjugate base, that halide. So they're going to be a very weak conjugate base. So they would be a good leaving group. And in fact, they are. And then to contrast that, a strong base is going to be a poor leaving group. Well, we learned about how hydroxide, sodium hydroxide, that would be a strong base. Okay, so that's not going to be a good leaving group. But as you'll see, what we can do is we can pretty easily convert a poor leaving group into a good leaving group by just slapping a hydrogen on it. That usually works pretty good. In that case, it would convert HO to H2O, which would be stable on its own. Water molecules are very stable, independently floating around. So that's one way to convert a poor leaving group into a good leaving group. All right, a little bit more about, again, hopefully all this sounds very familiar because we go over this stuff in Organic 1. That if you want to cause a reaction to proceed by the SN2 mechanism, then don't use a protic solvent. Protic solvents are not good for SN2 reaction mechanisms. So what do I mean by a protic solvent? That is a solvent that can donate a hydrogen bond. So by virtue of that, you know that a protic solvent is something that has to have hydrogen in its structure, and that hydrogen has to be connected to nitrogen, oxygen, or fluoride. That's how you can identify a protic solvent. But there are common ones: water, any type of alcohol, or any type of amine. All those would be bad solvents to choose if you want to drive an SN2 reaction. Why? Well, because those types of solvents are very good at stabilizing the nucleophile. They form a complex around the nucleophile and stabilize it. But you need that nucleophile to go and attack that electrophile. So you don't want to stabilize it if you want to drive an SN2 reaction mechanism. So they slow the reaction by solvation of the nucleophile. This stabilizes it, making it less reactive. Okay, this is just a diagram, what we mean by that solvation process, where the solvent, in this case, would be an alcohol, ROH. These ROHs are the solvent. And so if they donate hydrogen bonds to your nucleophile, then that nucleophile is going to be less reactive. Okay? So what you would use is a polar solvent, but you would choose one that's aprotic. Remember, anytime you slap a prefix A on the word, it means without, right? So aprotic solvents are solvents that do not have the hydrogen in their structure that's capable of engaging in a hydrogen bond. So polar aprotic solvents increase the rate of SN2 reaction by increasing the ground state energy of the nucleophile. So you've seen this graph already, but when I talked about it before, I didn't tell you what it's describing. It's describing what we just said. So in this case, if you chose a protic solvent, that would be like the black curve, because you stabilize that nucleophile. The black curve is where you have the solvent, because it's protic, stabilizing the nucleophile, so it's lower energy. Well, the result of that is you have a larger activation energy. Your delta G is bigger. The magenta curve is if I use a solvent that is not protic, it's aprotic. That's easy to get those confused. A protic solvent versus aprotic solvent. So you got to listen carefully. Or I try and choose my terminology so that I don't cause confusion, but sometimes it just slips out. So the magenta curve is when you have chosen a solvent that is not protic, okay? Because those will not stabilize your nucleophile. So your nucleophile is going to be higher energy, and then the result is that activation energy is smaller. So it leads to a faster reaction. There's less of an energy barrier there for it to overcome. Okay? So once again, if you just look at your different solvent choices, this is your reaction that you're monitoring. It's just a normal substitution reaction where the bromide is going to be your leaving group, and you're substituting that with azide. N3- is called azide. We don't talk about that nucleophile too much, but it can act as a nucleophile. And so it's going to attack this carbon that's connected to the bromine, substitute itself for the bromine. The leaving group is bromide. And so these are your different solvents. So your baseline is going to be methanol. That's protic. Water is also protic. It's a little bit faster. But then all these, the DMSO, the DMF, the CH3CN, that's called acetonitrile, and then HMPA, all those are polar solvents, but they're solvents that are not protic. They are aprotic. here's just the structure of HMPA if you're curious. You see that, it's polar, but it's not protic. And so it really accelerates the reaction 200,000 times what it was with the methanol. Okay. All right, so now that's all we want to talk about with regard to the SN2 reaction. Now we're going to focus on the SN1 reaction. So it's a different reaction mechanism. The steps of this reaction are different than the steps that occur in an SN2 reaction. First of all, what we want to just go ahead and lay out there for SN1 reactions is that they typically occur when you have tertiary alkyl halides. So that's where your electrophilic carbon is attached to 3 other carbons, 3 other alkyl groups. It's tertiary. The tertiary alkyl halides undergo substitution rapidly in protic solvents by a mechanism that's different than SN2. So that's what this just shows you. We know that it's a very different mechanism by this huge jump in reaction rate right here. That the methyl bromide versus the primary alkyl bromide versus the secondary alkyl bromide versus the tertiary alkyl bromide, huge jump, 1,000,000 or I guess 100,000 times faster when you go from the secondary to the tertiary. So that's an indicator that's a totally different mechanism. Okay. Well, the question is, well, why is that? Well, it's because of the stability of the carbocation. You must be forming the carbocation first in a unique reaction step. And then that carbocation goes on to react with the nucleophile in a different step, later step. So in this case, because we have multiple steps, one of those steps is going to be rate determining. And that's why it's just a first order reaction. So it's a substitution, nucleophilic, but in this case, it's unimolecular. So it's first order kinetics. And again, the reason why is because it happens in several steps. But the other thing that is a consequence of that is that the rate of SN1 reactions do not depend on the concentration of the nucleophile. Okay, so if you double the concentration of the nucleophile, it should not affect the reaction rate. You cut the concentration of the nucleophile in half, it should not affect the reaction rate. These type of reactions have they are not impacted by the concentration of the nucleophile. Okay. So remember, the way we talk about that with regard to rate laws is that the exponent is equal to 0. Every reactant in the reaction has got an exponent on it. But if that reactant concentration does not impact the reaction rate, then that exponent is a 0. And you know that because anytime you have something raised to the power of 0, that means it's equal to 1. Anything raised to the power of 0 is equal to 1. Right? So that's why the overall rate law then just doesn't include that term. Because when the exponent is 0, it just means it's like multiplying times 1. Okay, so for SN1 reactions, the rate is determined only by the concentration of the substrate. Okay, so then we got to remember, again, from Gen Chem 2 or from Organic 1 or both, that the reaction rate then is going to be based on the slowest step, the rate determining step. So the rate determining step, or abbreviated RDS, and so what is that step in this type of reaction? Well, that step is the formation of the carbocation. Okay, so you got this diagram, this reaction energy versus reaction progress diagram in your handout there, that you can see this proceeds by 2 steps. We got the first step, which is where the leaving group leaves, and you form that carbocation. So this is step 1. And then in a later step is where the nucleophile reacts with that carbocation. Okay? That's step 2. But the thing about it is that happens so fast because this activation energy is so much smaller when compared to this first activation energy. The activation energy was step 1. That this is really fast. It happens very rapidly. So the rate of the overall reaction is based on the larger activation energy. The step with the larger activation energy, that's going to be the slowest step. So this is like the slow step. So that's, as we said, after you form the carbocation, the nucleophile attacks rapidly from either side. So since it can attack from either side, if your substrate had some optical activity, so if it was R or S, you lose that. You end up with a racemic mixture because it can pretty much attack equally from either side. Now, again, as we learned about in Organic 1, That's skewed a little bit because that leaving group can kind of get in the way, impeding attack from that side, whatever side it's leaving from. But for organic 2 purposes, we're just going to say that, it can attack from either side equally. So you end up with a racemic mixture. Remember that would be, you still get you could get chiral centers in your products, but you get an equal amount of each enantiomer. So they cancel each other out. That's what we mean by a racemic mixture. Okay, so how do we know if an SN1 reaction is going to occur? It all has to do with the stability of the carbocation. If you form a stable carbocation, meaning if the leaving group leaves and what's left behind is a stable carbocation, then it's probably going to proceed by an SN1 mechanism. If the leaving group leaves and what would be formed is an unstable carbocation, then it's probably not going to proceed by an SN1 reaction mechanism. Now, remember that some carbocations can also be stabilized by resonance. And in particular, there's two situations we want you to remember about. The allyl cation and the benzyl cation. Each of those are resonance stabilized. So they, in the ranking, they're not more stable than tertiary carbocation, but they are a little bit better than a secondary. They're a little bit more stable than a secondary carbocation. So the point being is that, you're clearly going to get SN1 reaction mechanisms with tertiary. You're clearly going to get SN2 reaction mechanisms with methyl and primary. But in the middle here, the allylic and the benzylic and the secondary, then it's kind of a crapshoot. It depends on the other factors. Okay. They will react with both. So allylic and benzylic substrates react well in both SN2 and SN1 reactions. So, it'd be a little more challenging to figure out what's actually going on. You probably get a mixture of reaction products based on both of these reactions occurring, both these reaction mechanisms occurring simultaneously. Okay, so again, I don't think these are actually in your handout, but you can just refresh your memory. What do I mean by allyl and benzyl? So the allyl is when you have the positive charge that's next to a carbon-carbon double bond, because that positive charge can change locations. If the electrons in this double bond move over, then the positive charge changes sides. It goes from the right to the left. And so both of those, of course, in reality, we know that this is not occurring. The real situation is there's a superposition of both of these resonance forms is what really exists. But to help illustrate why this is a little bit more stable, this shows why that positive charge gets delocalized across the whole molecule, which means it's more stable. Anytime you can delocalize a charge, whether it be a positive charge or a negative charge, that's going to stabilize that species. Okay, and with the benzyl, there's even more resonance because you get the positive charge on the CH2 that's off of a benzene ring. So you got a benzene ring and then a CH2 that also has a positive charge. Well, that positive charge can move into the ring and then it can move around the ring. So because it has several resonance forms, it's also more stable than just a normal. Both of these would be you might think of them as primary carbocations because this positive charge is on a carbon that's attached to one other carbon. This positive charge is on a carbon that's attached to one other carbon. So you might think of them as primary, but they're not really primary because of resonance forms. So let's talk about the factors affecting, that just like we did with the SN2. How do these other things affect the rate of the SN1? Well, for the leaving group, it's the same as that we talked about for the SN2. So it's similar to that of SN2 reactions because the leaving group is closely associated with the rate determining step. So the SN1 mechanism will go faster, the reaction will go faster the better the leaving group. So poor leaving groups will go slower, the better the leaving group, the faster the SN1 reaction mechanism is. And so you can see that at the very fastest here is H2O. So what we're saying there is if we had an OH, if we had an alcohol group, let me just trace that on here. Let me just draw this. So what we're talking about here with the H2O is if we've got an R and there was an OH group, but then we come along and it's got 2 lone pairs on it, right? So then if we come along and one of those lone pairs grabs a proton, it becomes R, O, and now it's got 2 hydrogens on it. It still has 1 lone pair on it. It's got a formal positive charge. So this is a water molecule. So it can just dump those electrons onto the water molecule and we get the carbocation. And then the other product would be just H2O. So that's why, what you have When you have a bad leaving group like this, well, I can potentially turn it into a really good leaving group by just slapping an H plus on there. And we do that a lot. You'll see that. We talked about how the concentration of the nucleophile does not affect the reaction rate for SN1. Well, that's true because it's not part of the rate determining step. So it's not part of the rate law, and therefore it has no influence on the reaction rate. Okay, so the influence of the nucleophile in an SN1 reaction, there is no influence, bottom line. Okay, so what about solvation of the carbocation? Okay, that's going to be important. Anything that's going to stabilize that carbocation is going to speed up the reaction. So solvation of the carbocation is an important factor. It's an intermediate, right? That carbocation will react further with the nucleophile. So it's not the end product, it's an intermediate product. And so if you have a solvent around that will stabilize it, effectively what you're doing is you're lowering that activation energy. So it's going to speed up the reaction, bottom line. So the bottom line is that an SN1 reaction is going to go faster when you have strongly polar solvents. Okay, and to illustrate that, we have this little, again, this diagram that's not in your handout, but just look at it, pay attention to it. So if we just go from ethanol, pure ethanol, to pure water, and kind of take a couple steps along the way, like a certain amount of ethanol, a certain amount of water, it gets a lot faster when it's pure water. So, you know, starting with ethanol, that's our baseline reaction rate of, relative reaction rate of 1. But I put in a little bit of water, 40% water, it increases 100-fold. If I make it 80% water, it increases 14,000-fold. If I go pure water, it increases the rate by 100,000, factor of 100,000. Okay. Water is more polar than ethanol. Ethanol is also polar, but water is more polar. All right. So just recall that protic solvents do not favor the SN2 reactions because they stabilize the nucleophile. So the point is that sometimes you can pick a solvent to drive a certain reaction mechanism. So solvent choice can influence the mechanism of the substitution reaction. One solvent might drive the SN1, whereas a different solvent might drive the SN2. So, for example, predict which of the following substitution reaction was likely to be SN1 or SN2. So you've got the reaction there, and the transformation occurs. We substitute the OH with the Cl, and you know, I guess I already made the answer come up for you to write down. But you've got this allyl carbocation. Okay, this carbon right here, that's in an allylic position. It's on a carbon that's next to a carbon-carbon double bond. So this is an allylic position right here where that I'm highlighting. And so since that's going to have some, you know, enhanced stability, but also I've got a protic solvent and I've also got acidic conditions. So probably what's going on here is this H from the HCl is going to get dumped onto this OH group, converting it into a water molecule, which is a really good leaving group. So it's going to leave, and you're going to form a carbocation. And then the Cl minus is the source of the chloride. That's your nucleophile. So then it will attack the carbocation after you've already formed the carbocation intermediate. So because of these reaction conditions, I can pretty confidently say that we've got an SN1 mechanism here. This is, again, something that I know I talk about in Organic 1, but I remember I sort of make the commitment in Organic 1 not to give you any quiz or test questions on rearrangements. So starting in Organic 2, you can have questions that involve rearrangements like this. So I'll talk through it again. And the other thing I'll say is that I still will emphasize in the question statement that you need to consider rearrangement. So like there'll be the question, right? And I'll say in the text of the question, you should consider potential rearrangements for this problem. And that doesn't necessarily mean that there will be a rearrangement, but it just reminds you to think about those rearrangements. So let's talk about how that happens. So again, if I form this secondary carbocation right here, right, that's what it says. It says the secondary carbocation. And you can see that this carbon is attached to two other carbons. That's secondary. Well, what can happen is I can convert that into a tertiary if this just shifts over this highlighted methyl group in red. And the other thing about it is it doesn't have to be a methyl group. It can just be a hydrogen. Okay? So it can just be a hydrogen. That would be a hydride shift. So it's either an alkyl shift or a hydride shift. Pardon my chicken scratch. But if you move that group over to that secondary carbocation, look what happens. We produce this carbon that is a tertiary. So now it's a tertiary carbocation, which is more stable. Okay? So that's another situation where you could get an SN1 mechanism, but it's not readily apparent because the immediate carbocation formed would be secondary, but you could get a hydride shift or an alkyl shift to generate the tertiary carbocation. Okay, so that's fair game now. Because be on the lookout for that.